in this presentation, I'm going to go over and clarify some of the parts of your notes on amine A2-2 section of organic chemistry, and it's the beginning of amines, the properties and preparation. So at the very start, if you look at what the specification has, this is a section that has quite a bit of potential for synoptic type questions, because if you look at it, you'll see particularly around here, it talks things like the effect of hydrogen bonding on boiling point and solubility, and that links in with some of the work we did in AS. And you'll also look and see that a lot of the reactions of these are actually just tie-ins with bits we've done earlier on, and so there's a lot of sort of cross links with some of the previous organic chemistry. The definitions at the start are the usual ones. These are on the CA document, so these are the actual definitions. And when we look at amines, we see that there are a classification of amines in a similar way that we had with things like alcohols and haloalkanes, where we've got primary, secondary and tertiary. Now, with the amines, the classification of primary, secondary and tertiary is to do with the structure. And if you go and look at the structure of ammonia, which is this one here, you'll see that ammonia normally has 3 hydrogens. A primary amine is almost identical to ammonia, but in one position there's this R group. Now R stands basically for an alkyl group, that's CH3, C2H5 or bigger, some of those the carbon and hydrogen backbone groups. Secondary amines, you'll see again you've got the nitrogen and hydrogens, there's an NH group there, but this time there are 2 alkyl groups, and those 2 alkyl groups can either be the same, so that could be a CH3 and that the CH3, or they can be different. That could be a CH3, that could be a C2H5, or that could be a C2H5, and this one is C3H7, and so on. Tertiary amines then follow along, and they've obviously got 3 alkyl groups. So there's the CA definitions. So primary amine, only 1 carbon directly attached to the nitrogen, so therefore there's an NH group. Secondary, 2 carbons attached to the nitrogen, so it's an NH group. And then tertiary has 3 carbons, so therefore there's nitrogen with 3 alkyl groups attached to it. So on to the naming of them. Now, the general formula for the primary amines is CnH2n plus 1 NH2, so that NH2 is the primary group. And so you can think of it in 2 ways, and there's 2 IUPAC systems for naming amines. One is based on the fact that this is based on ammonia, so you'll see it's named as an amine, and then this is thought of as being an alkyl group attached to it. So you can see it'll be named as an alkyl amine. The other way of naming it is to think of this as being an alkane with an NH2 group attached to it. And when you talk about an NH2 group, we talk about amino. You'll be familiar with amino acids, for example. And so the NH2 group is the amino bit. So we can think of this as being methane with an amino group attached to it. So it'll be named then something like aminomethane, aminoethane, and so on. And the reason for the 2 variations is sometimes it's useful to use one naming, sometimes it's more useful to use the other. So for example, CH3NH2, so you've got the NH2 group and then a methyl group attached to it. It can be named in a number of ways. The 2 that IUPAC usually look for is that one, methylamine, which is handy, or as we said, think of it as aminomethane. Now, these can be useful in different situations. So, for example, this nomenclature, the methylamine or methylamine, is useful when you go to secondary and tertiary amines. Whereas this one here, the aminomethane, is actually useful if you come down to the situation here at the bottom of the screen. And that would be where you move the NH2 group along a chain. So if you have 3 carbons and then NH2 is based on propane with amino group, that NH2 is on the first carbon, so 1 aminopropane. But if you move the NH2 group to the second carbon, then it's also aminopropane, but then 2 aminopropane, and that's much easier to name than using this methylamine type system. So both are acceptable and both can be used. Secondary amines basically are where we've got the N and the H and then 2 alkyl groups. So as we said at the introduction there, the 2 alkyl groups can be the same. So for example, there's one with 2 methyl groups, so dimethylamine, dimethylamine. This one has got 2 ethyl groups, CH2, CH3, so diethylamine. And this is an example where you've got a methyl group in one position and an ethyl group in the other. And when they're listed off, usually list them alphabetically, ethyl before methyl, E before M, so ethyl, methyl, amine, so ethyl, methyl, amine. And then obviously if you've got other combinations, you could have ethyl propyl amine or butyl propyl amine, things like that. So you've got, depending on the number of carbons attached to it. Tertiary amines are where you've got 3 alkyl groups. So in this case, we've got 3 methyl groups attached to it. So then that would become trimethyl amine. And again, you could also have with tertiaries methyl diethyl amine or dipropyl ethyl amine, again, depending on the list. Okay. Structures. So there's, if you like, almost like a homologous series of them. So methylamine would be where you've got NH2 with CH3 attached onto it. That can be written as a displayed or a structural formula is that CH3NH2, and that's a condensed structural formula. Methylamine, as we saw, can also be called aminomethane, and then the skeletal representation is simply one bar to represent the carbon with an NH2 attached at the end of it. Ethylamine, 2 carbons with the NH2 group. The structural formula, condensed CH3CH2NH2, that can also be called aminoethane, and the skeletal representation is like that with the extra bar there to represent the extra carbon. Dimethylamine or dimethylamine, sometimes represent like that with the nitrogen and the lone pair of electrons. So sometimes structures will show that to emphasize that's going to be part of the chemistry of these. And then the 2 methyl groups there with the hydrogen attached to it. So that can be written as CH3, NHCH3. The skeletal representation of that would be NH with the 2 bars off it. And then trimethylamine, nitrogen with 3 methyl groups attached to it. Sometimes again that can be represented like that. That's to emphasize the lone pair of electrons that are attached onto it. And we'll see a wee bit later on with a tertiary amine, that lone pair is very available. So you see a very large representation of lone pair of electrons because that can be pushed up. That would then be named as NCH3, and then the skeletal representation like that. This is an aromatic one. So phenylamine. So phenylamine basically means a benzene group. So we've got our benzene ring there, and then the NH2 attached onto it. That can be represented as condensed structure C6H5NH2, and then 2 possible skeletal representations, one using the calculi type structure with the alternate double and single bonds, and the other using the more modern representation of the delocalized pi ring of electrons. Properties. Basically, properties are dependent on the fact that we can have hydrogen bonding. So primary amines and secondary amines can form hydrogen bonds between other molecules, so between themselves, and that means that they basically have higher melting and boiling points than similar MR alkanes. So if you imagine this was a non-polar molecule with the same MR, these would be much higher. And the reason for that, obviously, is because of the hydrogen bond being stronger. Now, this would be a possibility for a synoptic question. So don't forget, you would list off, if they're asking this, going back to what we did in AS, that the molecules would have van der Waals forces and hydrogen bonds, and obviously it's the hydrogen bonds that are the stronger ones that make them have a high melting and boiling point. So how does the hydrogen bond arise? Well, the lone pair of electrons on the nitrogen of the amines, so it's that lone pair of electrons there, is attracted to the delta plus of the hydrogen of a neighbouring amine molecule. So remember, it's between the lone pair of electrons and then the hydrogen on the neighbouring one, which is attached. That hydrogen is also attached to an electronegative atom, in this case nitrogen, and therefore the hydrogen bond forms between the molecules. The shape of amines is based on the fact that you've got 3 bonding pairs and 1 lone pair of electrons, so they repel each other. The lone pair will repel the bonding pairs more than these bonding pairs repel each other, and therefore takes up a trigonal pyramid shape. So that's based on trigonal pyramid. Because it's got a lone pair of electrons, it can readily accept H plus ions, so that means it's going to be basic in nature. If you put these amines into solution, they take hydrogens off the water. That leaves you with the amine with a N and 3 hydrogens in this case with a positive charge, and then you're left with an OH minus, and OH minus is normally associated with alkaline solutions, or an excess of OH minus associated with alkaline solutions, and therefore they tend to be basic in nature and alkaline solutions. Finally, to prepare amines, two methods. One would be if we start off with a nitrile. Now, the nitrile, you remember, has got the carbon triple bond onto the nitrogen. So to get that into being an amine, you need to get hydrogens onto that. So we think of that as being reduction, adding of hydrogen onto the molecule. In organic chemistry, the very good reducing agent we've come across, lithial, LiAlH4, or systematically lithium aluminium hydride, and that will add on 4 hydrogens. And you remember the representation of that is just 4 within a square brackets around the H. That's simply saying that this molecule supplies 4 hydrogens. We're not showing the details of how it does it. And then this carbon becomes CH2. It gets in excess of the hydrogens is saturated, and the nitrogen becomes NH2. The other way to prepare them is by substitution. So if you start off with a haloalkane and you react it with ammonia. Now, to do that, normally we have to do it in a sealed container because the ammonia is a gas, and if you heat that, it's going to evaporate. So even heating under reflux is not going to stop the ammonia from evaporating off. So we have to heat that in a sealed container. And we would get a substitution reaction. So for example, with 1 bromopropane and ammonia, the sort of reaction would be this. So propane would have 3 carbons and then the bromine attached onto it. And with ammonia, and under the conditions we've shown there, that'll substitute and give us NH2 and then hydrogen bromide. And that ties in with our AS2 work. So you can look back over the reactions of haloalkanes and AS2, and that again could be a possible synoptic question at A2.